Hello, everyone. Today we are going to study quantum mechanics with a simple model, particle in a one-dimensional box. So before the class, I would like to ask two warm-up questions. The first one is, when we're talking about the quantum mechanics, what's a scientist name coming to your mind? Einstein, yeah, good. Okay, so whoever coming to your mind, I have listed 5 great scientists here. They are Planck, Born, Bohr, Heisenberg, and Schrödinger. So the reason I list these 5 scientists because we are going to use their principles or their laws or their equations for our study today. The second question is, when we talking about the quantum mechanics, what equation or what theory do you think is the most important? Okay, great. Good. So no matter which theory do you think is important, so we are going to use a very important equation today, Schrödinger equation. The Schrödinger equation in the blue shade on this slide is a comprehensive one. It's three-dimensional and time-dependent. Today, we are going to use a simple case. So with the model, we are going to study a particle in a box to simplify the Schrödinger equation. Then we can solve the equation to get the answer. So the model we are going to use today is called particle in a box. It's a quantum mechanics approximation describes the translational motion of single particles. The single particle is confined inside an infinitely deep well and cannot escape out. So the particle is confined inside the one-dimensional space. We can call it as a box. Actually, it's not a box, it's a one-dimensional space. And for the real models, real case, we can consider or we can apply this model. For example, the electrons in metals or the electrons in one-dimensional nanomaterials. In these cases, we can approximately apply the particle in a box model to these real cases, just approximately. So today we are going to introduce the Schrödinger equation, simplified one, one-dimensional and time-independent. Then we are going to use the boundary conditions with our model to solve the Schrödinger equation to define wave functions and energy levels. After that, we are going to study the properties of the wave function and the quantized energy level of the particle and the probability density of the particle. After that, we are going to introduce two concepts, the zero-point energy and the separation energy between the two adjacent energy levels. At the end, we are going to introduce a real example with a real-world example of the exciting energy of the electrons and correlated to the absorption level of the photons of the molecules. Okay, for a particle freely move in a one-dimensional space and in parallel to x-axis, the Schrödinger equation can be simplified to the one-dimensional and time-independent case. It's like this. So here in this equation, sine is a wave function of the particle describes the probability distribution of finding the particle. It's a wave function of the particle describes the probability of the distribution of finding this particle. E is the kinetic energy of the particle. U is the potential energy of the system. M is the mass of the particle. And h bar here, h bar is a reduced Planck constant. H bar equals h over 2 pi. So now we are going to further simplify this Schrodinger equation with our model particle in a box. For a particle in a box, on the wall of the box or outside of the box, I mean, that means outside of the one-dimensional space, the potential energy U is infinity. Inside the box or within the one-dimensional domain, the potential energy is 0. So under this model, particle in box model, and we can write the Schrodinger equation in 2 cases. When the particle is outside of the wall or on the wall, the U is infinity, so the psi is 0. Because U is infinity, here is this term, the right hand side term is 0, and the psi is 0 everywhere. That means the particle is impossible to be on the wall or outside of the box. Inside the box, because the potential energy is 0. That means we can remove the U from here for the case of the particle inside the box, right? Here, that means inside the box, x greater than 0 and smaller than L. In this case, either x greater or equal to L or x smaller or equal to 0. So in this case, because the wave function is 0, we are not interested in this. We only interest the part because the particle only appear in the box. So outside the box, we don't need to consider it. So we only need to consider when the particle is inside the box. The Schrodinger equation can be further simplified like this. So with this equation, we are going to apply the boundary condition to solve the energy and the wave function with our boundary condition. Okay. So how to solve this equation? It needs some special mathematical techniques. So I have written the full note about how to solve this equation, this Schrodinger equation. In this case, the differential equation is called the second order linear and homogeneous differential equation with constant coefficient. So it needs some special mathematics skills. I have written 4 notes here, the 4 procedure of solving this equation. I covered some steps here. I want you to practice after class. Just practice about how to solve this equation. And it's good for you to to practice the mathematical skills of solving the differential equation. So the time, so because this will be exercise 1 after the class, and now let's go ahead. So after solving this Schrodinger equation, we can get the solution of wave function like this. Psi wave function is C sin kx and D cosine kx. K here is a new term we defined as a square root of 2me over h bar squared. So the definition this way is just for the convenience of solving the Schrodinger equation. And we are going to use this K a moment later. Now we can leave it here right now. In this solution, C and D are unknown constant generated when solving the Schrodinger equation. There are unknown constant. To figure out C and D here, we need to apply the boundary condition of the particle in a box in a box model. So because when x, because if the particle is on the wall or outside the wall, we don't need to consider about the outside. We just consider the on the wall. On the wall, that means x, in case of x is 0, and psi x will be 0. Okay, the boundary condition. And on the wall, that means the wave function will be 0 because potential energy is infinity, so the whole wave function will be 0. Another case, if the particle is on the right side of the wall, so x is L, it's also 0. The wave function is also is 0 on the both walls on the walls on the both sides. So now let's apply the first boundary equation. So in that case would be psi 0 equals C psi 0 plus D cosine 0. That's the first boundary condition. We know psi 0 is 0. And sine 0 is 0. Cosine x is 1, right? To balance this equation, that means the D must be 0, right? D must be 0. So D must be 0, so we can remove the second term of this wave function. We don't need to consider the second term, right? We can remove this. If D is 0, and C must not be 0, because if both C and D is 0, and the wave function will be 0 everywhere, it does not make any sense. So C must not be 0, only D is 0. Okay, so we can determine D, the constant D, with the first boundary equation, boundary condition. Okay, so now let's apply the second boundary equation, second boundary condition. Second boundary condition is psi L equals C sine K L, right? Okay, follow here. Psi L is 0. And just now we know C must not be 0. C must not be 0. That means sine KL must be 0, right? Sine KL must be 0. How to satisfy sine KL is 0? That means the KL must be integer numbers times of pi, right? Integer number times of pi. That means KL must be n pi. And n is integers from 1, 2, 3, and so on. Here, we need to make a note here. N is not allowed to be 0. Must be from 1, the lowest number of n must be 1. It's not allowed to be 0. Because if n is 0, and k will be 0. If k is 0, and the wave function will be 0 everywhere. Does not make sense again. So n, the lowest number of n must be 1, from 1 and to infinity, integers. Not allowed to be 0 for n. Okay, if KL equals to n pi, that means the k can be expressed as n pi over L, right? If k is okay, we can write it here, and k equals to n pi over L. We're going to use it afterwards here. And if k is n pi over L, we can replace k here in the wave function. We can write it as sine n pi over L x, right? Okay. And so now in this wave function expression here, we notice that C is still unknown. C is still unknown. It's a constant. It's a constant generated when solving the Schrodinger equation. It's still unknown. How to solve C? To solve C, we need to. Okay. To solve a constant C, we need to apply a law. It's called Bowens Law. According to the Bowens Law, the probability density of finding a particle inside the box, inside the domain must be 1. The total probability density of finding the particle inside the box is 1. The probability density, because the outside of the box, on the wall of the box, the wave function is 0. That means probability density is defined as sine x squared. If we integrate from 0 to L inside the box, and dx must be 1, right? And we can substitute the sine x, the wave function, with C sine n pi over L x. And then we can obtain expression as the blue text on this slide. So to solve this integral equation, we also need some mathematical skills to solve this integral equation. So this will be exercise 2, the second exercise after class. I have written the full steps, 4 notes of solving this integral equation. And you can practice after the class under the hints I provided on this slide. That's the sine theta square equals to 1/2 1 minus cosine 2 theta. Yeah, just based on this the basic function. And after solving this integral equation, we can get a solution of C is square root of 2/f. And we can substitute C to the wave function here, and then the wave function now can be written as square root of 2/f here. Now the wave function is solved. So now the only variation is x now, n pi l. L is the size of the dimension of the space, the x, the length of the box. And now we also know the k must be can be expressed like this. To correlated to the number n here, number n must be integers from 1, 2, 3, and so on, the integers. So we can give a subscript here for kn to correlate to the n here. Okay. So based on these two expressions, we can obtain the expression for the energy level En. From here to here is easy, so it's just to solve these two equations to get the E here. So it's simple, so we don't need to derive it in detail. So it's a very simple derivation. Ken would be n n square h square h and l square. So now we have the two equations for the wave function psi and the energy level here. N is, sorry, 1, 2, 3, so on. So because n is only allowed to be integer numbers, that means the energy level is not continuous. It's quantized. It's not continuous. It's quantized, right? So because n is only allowed to be integers, not allowed to be the other numbers. So now we have both the wave function and energy level expression here. That's the most two important equations for studying the other knowledge with this particle in box model. So next we are going to introduce the property of the wave function, property of the energy level, and the probability of finding the particles inside the box. So let's talk them one by one.